सुभान अल्लाह।
ड्रोन है ना। अच्छा लैंडिंग के लिए आ जाएगा अभी नहीं? नहीं अभी नहीं। 40 सेकंड। विकास भाई फिगर ऑफ 8 बनाने हैं। बड़ा सा बना लो। बड़ा सा बना रहे हैं, बड़ा सा। नहीं कोई मसला नहीं है, वो मैं करा दूंगा। बॉयज लैंडिंग साइड पे हो जाओ रोड से।
1 मिनट 30 सेकंड हो गए हैं। हटो। बिस्मिल्लाह। सुभान अल्लाह। सुभान अल्लाह।
Hi everyone, my name is Daud Khalid. I am a final year undergraduate student of mechanical engineering. I am the captain of Team Ascensor Technofest 2025. I have the lead for wing design and fabrication, computer-aided design, aerodynamic stability, control and flight testing. Thank you.
I am Zainul Hassan, undergraduate student of mechanical engineering. I have the lead for motor driver mechanism, linkage design and interfacing control system lead, and the iterative calculations for the control surfaces.
My name is Shalal Hassan Sayyed. I'm third year undergraduate mechanical engineering student, and I have lead in fuselage fabrication and design, literature review and research.
Hi, this is Evan Nadeem, third year undergraduate student of mechanical engineering. I have the lead for airfoil selection, empennage design and fabrication, and CNC manufacturing.
I am Astaruddha, third year undergraduate student of electrical engineering, and I have the lead for microprocessor and interfacing, algorithm design and software configuration.
My name is Joseph Berkeley. I'm third year undergraduate student of mechanical engineering, and I have the lead for computer-aided design, CFD analysis and automation. Individual components, their quantity and weights are mentioned in the table. The total weight of the UAV is 2.3 kg. The weights of the individual components and their position in X, Y and Z axis is displayed. The bottom left corner of the firewall is taken as the origin. The wing parameters are shown. The horizontal tail parameters are shown. The vertical tail parameters are shown. The schematic shows the origin and the position of CG in X, Y and Z axis. Analytically, CG is determined using XFLR software and it lies near quarter chord. Wing surfaces were developed using NACA database. It was cut through CNC, reinforced with carbon fibers, 1 mm balsa sheeting and thermal sheeting. The tail surfaces were also manufactured using RIP configuration and further reinforced with carbon fibers and balsa. T-tail configuration was used. Wing and empennage are shown. Fuselage is CNC cutted through plywood. Payloads are made from balsa. Boom couplers and firewalls are manufactured through laser cutting of prospect sheet. 3D printed couplers are used. Firewall and landing gears are attached to fuselage. The boom is mounted to empennage using coupler. The fuselage and empennage assembly is displayed and the wing mounting process is shown. The animation visualizes the component placement in UAV. Monocoque design was preferred for the fuselage because of its ease of fabrication, high strength to weight ratio, low material consumption and overall economy. T-tail configuration was used for better stall recovery. Velcro is used to fix the components. The engineering diagrams, structural configuration diagrams and wire diagrams are added as per requirement. The final assembly diagram is also provided. This is the rendered image of our final UAV 3D model, and this is our final UAV. The lift, drag and moment were calculated using three approaches: numerical, analytical and experimental. The design constraints are as shown. A 12x6 propeller was used according to the manufacturer catalog. The design objectives are as shown. The numerical analysis is done using trivial formulas. The lift came out to be 70.74 Newton. The Clark Z airfoil was used for wing. The reference graphs are taken from NACA database. A theoretical results are idealized value that gives lift over the wings. XFLR, ANSYS and SolidWorks software were used to obtain analytical results, and they are displayed. Viscous SSTK omega was used as the flow model. The boundary condition was given by setting the inlet velocity to 25 meter per second. The stall characteristics of Clark Z and NACA 0012 are shown. The diagram shows the flow separation from the airfoil at 20 degrees angle. The graphs of CL, CD and CM are plotted and shown. Similar analyses were performed using SolidWorks and ANSYS. The CFD results are illustrated. Experimental results obtained by wind tunnel testing on a 3D printed model of the UAV are shown. The results from the approaches were compared. Analytical and experimental approaches give realistic results in comparison to theoretical results due to the factor of 3D wing over a 2D airfoil and the wing's aspect ratio of 6 over the infinite airfoil. Stability analysis was performed in XFLR. The UAV returns to its stable position when disturbed in longitudinal and lateral direction. NACA standards were used to calculate aileron parameters. Actual length of the rudder is equal to the horizontal tail span instead of the recommended value of 0.6 times the span of the to increase the stability. Width of the rudder was based on the root code for this configuration. The plan for mission 1 is displayed. For target detection system, Raspberry Pi 4B Plus was selected as it is easy to run OpenCV Python version on it. PixHawk was connected to the Raspberry Pi through 6-pin FTDI cable to 6-pin telemetry cable. Raspberry Pi is powered through auxiliary output of PixHawk over 5 volts. The camera is connected at the lower surface of the fuselage to give better view for target detection. Telemetry information such as GPS location, altitude is sent and received through the serial ports of Raspberry Pi using the Mavenlink protocol of ArduPilot implemented by DroneKit Python library. The dimensions of the hatches and payload bay is given. The animation shows the payload drop mechanism. The real-time demonstration for payload mechanism is shown. This section displays successful target detection and payload drop. BLDC is used as propulsion system and its specifications are shown. 5000 mAh lithium polymer battery is used and the specifications are shown. Emax servo motor was used and the specifications are as follows. 60 amperes electronic speed controller was used and the specifications are as. PixHawk was used as flight controller. Raspberry Pi was used for image detection. Battery is positioned at the bottom compartment of the fuselage. Fuse and switch is connected with positive terminal of the battery along with this PixHawk power module. The bus wire of the power module is connected to the PixHawk and the other end is connected to the ESC. Here it is connected with the BLDC. The BEC output of the ESC is connected to the main out of the PixHawk along with other servos. The telemetry is connected to the telemetry 1 port of the PixHawk and the Raspberry Pi is connected with the telemetry 2 port. The servos of payload are powered by the aux out of the PixHawk and their PWM terminal is connected to the Raspberry Pi 4B. The radio receiver is connected to the RCIN pin of the PixHawk. GPS is connected to the PixHawk at GPS and I2C ports. GPS is mounted at the top. Camera is placed at the bottom. The safety switch is mounted along the power switch. Fuse and switch diagram is shown. For better understanding, a detailed wiring diagram is shown.
Electronic assembly was previously described in the component placement and wiring diagram section. Soldering was mainly employed for the permanent electrical connections, and XC90 connectors were employed for the easy handling and the disassembly of electronic components. Electrical components such as power module and fuses were floating, and the switches were glued to the fuselage body. This was done carefully so that the glue didn't stuck the switch, and solder connections were well insulated to avoid any short connections. Picksock was mounted onto the dampers, and the special lightweight casing for the Raspberry Pi was 3D printed, which was bolted to the fuselage.
Safety, we use the combination of fuse and switch. As shown in the schematic diagram, we use 2 fuse and 2 switches in parallel combination. This is to improve the current rating, as components of our desired rating are not available in the market. We also added the required fail-safe system to the UAV. If the controller and receiver connection is lost, the UAV will enter the fail-safe mode. The video clip shows that our fail-safe system is working. Picksock is used as flight controller. Mission Planner software is used for configuration of Picksock as Pickswing. It has built-in sensors, that is compass and accelerometer, and GPS is added externally. Calibration of different sensors is as shown in the video. The flight modes manual, stabilize and auto are set through Mission Planner at channel switch. The flight path is set through Mission Planner for autonomous flight as shown. Performance parameters are calculated using displayed formulas. The Mission 1 parameters are displayed. The completion time for the mission was calculated by defining a path in Mission Planner. The distance calculated was divided with velocity to obtain the time required to be 53 seconds. Mission 2 parameters are shown. Target accuracy was determined experimentally and it came out to be 70%. The power consumption calculations are shown. The battery discharge is calculated for 100% and 80% throttle. The battery consumption test was performed at 80% throttle. It took 8 minutes for the battery to discharge. The engine thrust test was performed. A maximum thrust of 2200 grams was noted. At 100% throttle, it is approximately equal to 22 Newton. Chassis test was performed with 2.5 kg loading. The fail-safe test was performed. The mission systems and CG balance test was performed. The total weight of the UAV is 2.3 kg. The product distribution tree approach was used for the selection of important components. The detailed breakdown of cost is provided. Due to the unavailability of carbon fiber sheets in COVID, simple fuselage design was fabricated from ply. Circular hatches are replaced by rectangular hatches to reduce weight. Circular hatches tend to bend under load. We have designed an electronic speed controller for BLDC motor with MOSFET switches in 3-phase H-bridge configuration and Arduino Nano as microcontroller. We also designed a radio controller and receiver using STM32 as microcontroller. The designs were fabricated on the PCB. The details of the design hardware and software is attached in RAR file.